So in this lecture, we're going to take a look at a proof that relies on the generalized pigeonhole principle that we just discussed. And I've just restated it here just for a quick review. It just says that if we're taking n objects and sorting them into m boxes, there must be at least one box with this many objects in it, right? And over here, the way I think of this in my head, right, I think it's the number of objects that goes in the numerator, and the number of things that are being sorted into, the number of categories, that goes in the denominator. So this is the statement that I want to prove, right? I want to start off by letting x and y be finite sets with the same number of elements. That's what I've illustrated over here in this little diagram. And I want to suppose that f is a function from x to y. All right, so what I want to show is that if f is 1 to 1, that f is 1 to 1, if and only if f is onto. So in other words, if the function is a mapping between two finite sets that are the same size, then 1 to 1 and onto, they go together. You have to have both of them. Okay, so remember this is an if and only if, right? With an if and only if statement, we actually have to do two proofs. First, I have to show that if f is 1 to 1, then it's onto. Then I have to go the other way. I have to show if f is onto, then it's 1 to 1. Okay, I'm going to do this way first. I'm going to assume that f is 1 to 1, and I want to show that it's onto. And I'm actually going to do this by contradiction, right? So I'm going to assume f is not onto. Right, so what does that mean? Well, remember, an onto function is one where every element in the codomain, in the y set here, has to get mapped or paired with something in the x set. So by saying it's not onto, that means there has to be at least one thing in the y column that does not get matched with something from the x column. Right? So that grayed out one I'm going to take out of the mix. So we're going to take all the elements from x and map it into the elements that are left on the y side. All right, so what do I have going on here numerically? Well, if x has n elements, then I'm mapping that into now n minus 1 elements. Okay, so now here's where this generalized pigeonhole principle is going to come into play, right? The generalized pigeonhole principle says, remember this is objects divided by categories. So this is going to be ceiling n over n minus 1. And once you think about n over n minus 1. N minus 1 obviously is smaller than n, right? So I don't know exactly what this number is, but I know that it's going to be greater than 1 and less than 2, right? Which means this ceiling is going to be 2. All right, so what does that mean, right? We'll go back to the pigeonhole principle. This says that there is at least one value in the y column that gets two values from the x column mapped to it. And that violates our assumption that the function is 1 to 1. Right? There's our contradiction. Right? Because we've reached a contradiction, our assumption here that f is not onto is invalid, and f must actually be onto. So now we need to go the other way. Right? I'm going to assume that f is onto. I'm going to show that that means it has to be 1 to 1. And I'm going to do this one by contradiction as well. So I'm going to assume f is not 1 to 1. All right, so that means that there must be two x values that get paired with the same y value. Assume it's these top three here that have that. So now where does this leave me? Well, now there's n minus 1 elements over here, but only n minus 2 over here, right? And now I'm stuck. There's no way I can map n minus 2 elements to n minus 1 elements in such a way that every one of the n minus 1 get mapped with something. So that contradicts our assumption that the function is onto, which means our initial assumption here that f is not 1 to 1 must be invalid, right? And the function will be 1 to 1. So this brings us to the end of our discussion of combinatorics and counting methods. In the next chapter, we're going to switch again, right? As I've said before, this is a survey class, so we do kind of bounce from one topic to another. In the next section, we're going to switch over and start talking about something called graph theory.